Hello and welcome to another video. In this video, we're going to be working on validate binary tree nodes. So in this problem, you have a binary tree with nodes labeled from 0 to n-1, where node I has two children, left child and right child, and you want to return true if all the given nodes exactly form one valid tree. If node I has no left child, then it will be -1. Similarly, for the node not having a right child, it will be -1. Let's make this a little bit bigger, actually. And let's go through it. So for this first example, so essentially node at index, whatever node this is, this will be the left child and this will be the right child. So let's kind of like draw it out. So here they're saying that the first node is at index 0 and that's the root. So node 0 has left child 1 and right child 2. And then node 1 has left child -1, right child -1. Node 2 has left child 3, right child -1. So it's 3, -1. And 3 has two null nodes. And so this would be a valid tree, right? So let's go to the next example. They're saying the root is node 0. So for node 0, the left is 1, the right is 2. And for node 1, the left is null, and the right is 3. And then for node 2, the left is 3. So you see there's a cycle here, and the right is null. And then for node 3, these are both null. So there's a cycle here, so this is a problem, right? Because both 1 and 2 point to 3, so this would be invalid. And for the last one, the root is 0 again. The left is 1, the right is null. And then for 1, the left is 0, so it's a cycle because this points back up to 0. So essentially, we have to define like what a tree is, first of all. Right? And there's a few ways to do this, but yeah, let's define what a tree is and let's figure out what to do. So a tree, and this is also kind of similar to, I think there's a problem called like make a tree from a graph. It's kind of similar. You could do a union find here, but we're just going to do a normal tree traversal. So a tree has a root, has no cycles. You can also count the number of connections, but we're not going to do that since we're going to do normal DFS, so we don't really care about that. So it has a root, has no cycles, and then each child, or I guess like every node, is connected to every other node, right? So if we do a traversal from the root, we should be able to hit every node with no cycles. Yeah, pretty much. So yeah, so if there are no cycles and every node is connected, then we have a valid tree. So the problem is, or at least one of the problems is, like, let's say we do have this like left child and right child thing. Like, let's say it's even this. So first of all, how do we figure out, like, looks like once we get the root, we can just do like a DFS, but how do we get the root? So let's say we have something like this, right? So this would be like for the first one. So essentially you have something this with it, we have the left child and the right child. How do we get the root here? So notice the other thing is, I guess that we didn't mention, we can write as well. So for root has no parent, right? The root node has no parent, meaning the root will not be in here or in here, right? No node will point to the root. So whatever node is missing from here is going to be the root. And how do we figure out what node is missing? Well, that part's pretty straightforward. We can just take the left and the right, and you can either like look through it, or you can just combine them and make them a set, right? So you can just make them a set, and then what would happen here is, let's say you do make these a set, so all the values would be like -1, 2 is in here, 1 is in here, and 3 is in here, so and in the set. And then you just look like, okay, I know I have nodes 0, 1, 2, 3, 4, or whatever it is, 0, 1, 2, 3. Let me just go through 0, 1, 2, 3, and then whatever number is not in here is my root. And then if like all these numbers are in here, then this is already invalid, right? Let's say the set somehow did have 0, 1, 2, 3. Let's say it did have like these numbers when we made our stuff a set. If it had everything, then this would already be invalid and we get to return false. So that's one case. Now another case we can return false right away is, so let's say this had like something like this. And we were like, okay, well, 1's not in here, so 1 is our root. But the problem is there's a bunch of numbers that are not in here. So this set, what we're going to do is we're going to make a set, and then we're going to get rid of -1 if it's in there. And then the rest of the set has to be n minus 1, right? There has to be one number missing, and that's it. So if n is 4, there has to be one number missing. So it has to be like 0, 1, 2, or 1, 2, 3, or whatever it is. So those are the things we're going to check for is number missing is root and set length equals n minus 1 after we get rid of the -1 that was in there by turning it into a set. So if one of these is false, then we can return false right away because there's either multiple roots or there is no root and either one is false. Okay. So once we have a root, then it's pretty straightforward. Essentially, all we have to do is let's go back up to our example. Let's say this is our stuff, right? So let's actually copy like this left and this right, let's say. Now we just need like a straightforward DFS where, so if this is like one of them, and this is the other one of them. Yeah. So now we know like where to start. Let's say in this case we start at node 0. Now we just pass in the index. We just do a DFS of whatever node we're at, and then we're gonna create another set of like visited nodes, right? Essentially. So we want to check that we visit every value once and only once. So we'll have like a visited, and then what will happen is let's kind of walk through it, right? So we're gonna start at 0 and we're gonna say, okay, well, what are its children? So its left child is, so we're kind of like drawing it out. Its left child is 1, which is not -1, so it's there, and its right child is 2. So let's add both of those to visited as well as the node itself, and you can add wherever you want, like to visited. Either place is fine. Essentially, you can either add as you visit, or you can add right away. I guess what we could do is we can add as we visit. That would also be fine. So essentially, to visited, we want to add the node, right? So we're going to add the node. So we're going to add the root. So we're going to add 0 to visited, and then we'll just like go left. And then when we go left, we're going to go over here, and we're going to say, okay, well, this node has children -1 and -1, and you could even recurse. So you could recurse, and then your base case can just be like, if your index is -1, then return something, right? That's also fine, essentially. And pretty much what you want to do is you want to recurse down this whole thing, like a normal tree traversal, right? You recurse down this whole thing as far as you can, and you just check for the node I'm on, have I visited it before, right? So whenever you're at a node, you just check like, is it in my visited set? And if it's in your visited set, that means you've seen it twice. So you just want to return false. And if you have a valid node, you just return true, right? So you want to return like the node hasn't been visited, and then you want to also make sure that for a given node, the left and the right also return true. So you're basically just returning, saying like, have I seen this multiple times? Essentially like a normal tree traversal, except for a tree traversal, instead of having like nodes, you just use an index. So it's pretty straightforward. So -1 will be null, so we can return true as in that's like a valid node, and then anything else, we just have to check our visited set. Then once we do that, once we check our visited set, what we have to do in the end is we have to make sure like our DFS returns true, and we have to make sure that our visited set actually has every node, right? So what we're going to do is we're going to check that the length of our visited set equals n. And if the DFS did return true and the length of our visited set is n, then you return true. I'm not exactly sure if you have to check for both, but I'm just going to do it. Maybe you can avoid checking for this if you checked for all the nodes beforehand. I think it no, actually, I think you do, because you might have some like disconnected nodes. Yeah, so you can easily have like all the nodes beforehand, where you could say like, yeah, there was a valid root, all the nodes were in here, but you might have some disconnected nodes. So that's pretty much it. All you do is you just make sure that you DFS, and then you add every node to the visited set, and then if it's already in there, you return false, and then you just return like this node's value hasn't been visited, and its left and its right hasn't been visited, and that's pretty much it. So now we can code it up. So essentially, we're going to start with getting a set of nodes, so we can just say like nodes equals set, and then we're just going to like add these two lists, left child. Or I guess what we could do is we can add them to the set. I think this would take up a bit more space technically if you add them together. So I guess we could add that. So we could say like nodes equals set, and then we could say like for val in left child, if val does not equal -1, let's say, nodes add val, and then we do the same thing for the right child. You could make this shorter, but if you made them shorter, you'd have to concatenate the list, which is probably not great. So for valid and right child, same thing. So now that we have those, we essentially have it all added. So now remember, we have to check if we actually have a root. So we can just set a root value equal to like -1, and we can just traverse the set. So we can just say like for I in range. So there has to be an I value that's not in here. And we can also say if length nodes does not equal n-1 here, we can return false straight away, right? Because there has to be every node except for the root. So if this should be length. So essentially for like 4 nodes, it would have to have like, 0, 1, 2 or 0, 1, 3 or something. There has to be one missing node. If that's not true, then we can return false straight away. Now we can check for I in range n+1. And then we can say if I not in nodes, then let's make that equal to the root. And let's just break. Should be I. So there we go. Now we have our root. Now we check if we actually got a root. So we could say if root equals -1. Oh, it's also return false. So now we have our root, and we made sure that like every node is actually in here. But now we have to actually make sure we can connect them. So to make sure we can connect them, we're gonna redefine our nodes. So we'll make an empty set again, and then we'll make a DFS function, right? So def DFS index, and we'll just say like if index equals -1, right? Null node. Let's just return true. Yeah, let's return true. And then let's actually go and like check the left and the right and stuff, right? So pretty much what we have to say is we have to also check if the value hasn't been visited. So actually, now that I'm thinking about it, you can't get the value directly. Actually, no, you can get the value directly. It's passed in. Yeah, never mind. Okay, so yeah, so we have to say, we can say like if index in visited, or nodes, I guess. Let's just return false, right? And then pretty much what we have to say is let's just return the DFS into the left and the right. And I don't think there should be an infinite loop, because if you have like -1 and -1, this should just return straight away, right? So we can just say return DFS of left child index and DFS. I guess it would be like this: left child index and DFS right child index. So pretty much just return both of those. We are forgetting one thing. So we did forget to add the node to visited. So let's do that as well, right? So visited nodes.add index. But yeah, so we just recurse left and right, make sure that they are both fine, return. And now we simply have to call our function, right? So we can return DFS. And remember, in our picture, it always started at 0, but the root doesn't necessarily have to be 0. So we'll pass in whatever index the root was, so DFS root. And after we're done, the length of nodes should have every node in here, right? So if every node is in here, then it's valid. Otherwise, we miss the node, so we have something invalid. Let's take a look. See if we have an error. Okay. And so it does work, and it's reasonably efficient. Yeah. I'm not sure how I can improve the memory, but the what's it called is fine, right? The time. As far as the memory, I don't know how we can improve it, honestly. I'm kind of curious about it, but whatever. Let's just go through our solution in the time and space complexity. So for the time, first thing is we go through this left and right child, right? So that's going to be like O of, let's call that L and R, so O of L plus R. And we make the set, and yeah, so that part is L and R. Then we go through our N again. So I guess we'd have to like add N as well. They do tell you, I think. Let's take a look at the constraints really quick. So L and R are less than N guaranteed. So if L and R are less than N guaranteed, then they would just, N would be bigger than both of those, so it would just be O of N, because you are going through L and R, but essentially it's just O of N. And then we are going through it one more time here. So that's still O of n. Then we make our empty set, and then we do a tree traversal. All right, so we do a tree traversal, and a normal tree traversal is O of n time, right? And for the space, so we do have this like visited set where we have every single node, so that can be O of n already. And then also, obviously, their cursive call stack for a DFS of a tree is worst case n, assuming it's completely unbalanced. But the visited set will supersede that usually, because like it'll just be length n, which will be every single node. So yeah, it's going to be something like this. And yeah, I think that's going to be all for this problem. Not too bad. Basically, just have to realize how to traverse this like a normal tree with a route that you can find, and it's pretty straightforward. And yes, that's going to be all for this one. And if you did like this video, please like it and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.